considered the formula but in that term, I don't put the degree m. Only it was such term. Now we consider the same formula, but with such a degree. Last time we saw that U is on the drawing gamma sub E equal phi E. But now I want to stress another property, this slightly corrected formula. This property is such kind that not only U will be coincide with functions phi sub E, but also will be coincide with so if we have some functions here, and I want that not only these functions on drawing gamma E, this is, I remind you, gamma 1, gamma 2, gamma 3, gamma n. Gamma E. Not only functions such constructions coincide with phi on the such drawing, but all derivatives, these functions, normal derivatives, these functions, coincide with normal derivatives, these functions on this drawing till number k sub E minus 1. It is yes, thank you very much. It is easy to explain why such properties appear. This term, if I have derivatives till number m, it will be 0 on all the boundary. Omega is all drawings, union all these drawings. So it will be 0. It is evidently, this is 0 because this large degree. But here I explain why. I rewrite this first term in such way. For example, V1, K1 plus omega all other terms are all other terms here all other terms in denominator, but this is phi plus quantities order relatively omega 1. Omega 1, when we consider in this vicinity gamma 1 is small. This is small, more higher order. In denominator, we just have the same, but this is phi plus it is easy to see. Or in more detail, I can rewrite so phi plus but I took only first only first term here I took first. It is not distress conversation.
HWI is an equation.
Yes, as example. And now we can see that this is phi plus O, because here phi
what is A and B? More general
A, this is that term. I took first one, other noted by A capital. Here took only first one, other noted B capital, all other. Yes. Then come to this form, then this is small order omega 1 K1. This is such symbol shows that this is small quantity. But later I add and distract phi, and after go to one line, common to
denominator.
Common to denominator, yes. common denominator, yes. And we see that this is small quality because such calculations, xn minus xn is n. Here is such algebra when we're working with such quantities. And if we one, everywhere phi1. And if we look what is it on gamma 1, this is phi gamma 1. Of course, we can do the same with E equal to, and so on. And due to that, when we shall take derivatives from this term, this will be after every derivative. It will be, if I shall take derivatives from quantity omega k, it will be derivatives order omega k minus 1. So we shall have derivatives of the first, we shall have, the first derivative is derivatives from phi sub 1 and quantity, small quantity order omega in degree k 1 minus unit, so on. And only we shall receive 0 degree here after derivatives. We get something else. That property let us to use that kind of formula in different situations. One of them I shall show you. Suppose I wanted to construct such functions which, for example, on that side is minus 1. This, on this drawing, plus 1. But inside such domain, for example, this is circle, I wanted it will be polynomial order degree in all this domain, any polynomials. And in what way I can construct such functions? Suppose omega 1 is equation left part of this rectangle. Omega 2 equation this part of the rectangle. We constructed such functions. But suppose this is then I can write equations of this circle, this domain, using idea which we see in academician Alexandrov example. I can take it will be 0 in all this domain. But if I take in some enough high degree, it will be sigma 3. This will be equations all this domain. And in such kind formula, I wanted that functions which will be here is equal unity, but I nothing new about these derivatives. And here I nothing new. But here I want that these functions will be coincide with those derivatives, suppose till second order, for example. Then I shall construct functions such way. Minus 1 omega 1 plus 1 omega 2 plus Pn omega 3 in degree 3. And here plus omega 1, omega 2, omega 3, for example, in such way. This is union, equation of union, these three drawings. So if I shall take derivatives till order 3, it will be 0. Here, it will be 0 till derivatives order 2. And this is construction such functions, which is plus 1 here, minus 1 here, and some polynomial inside. For example, this is polynomial, harmonic polynomials, which satisfy Laplace equations. Then, if I shall consider the equations, then here it will be, when I take these constructions, it will be 0 inside. Невязка, как сказать, а я забыл, невязка. Невязка. Отклонение. Вот я подставил сюда, получил какое-то отклонение.
Difference pair. Это торговый термин.
Yes.
Difference pair.
Yes. So in this domain, this equation will be exactly satisfied. And I can now only approximate to exact solution working in this side. This is simple example in what situation when we can use such, but sometimes, often it can be happen when those try work out experimental data. What, they knew something about functions which we considered maybe in some domain we knew this behavior, and using such formula we can work out experimental data in some situations. This formula can be considered as a bunch of functions which satisfy boundary conditions if we knew them, or can be considered as a structure of solution some problem if you have some differential equations and some boundary conditions. This way we can satisfy these conditions, all these conditions. But then can try found definite component, this bundle, to satisfy the differential equation or system differential equation or so on. This structure, we can see that this structure have property fullness, because we can consider this as such formula, and this is that term, and for any functions which satisfy boundary condition, and for any solution of this problem, we can find such functions phi. Look here. If we find from here phi, we receive such formula. On the boundary, this is 0 because exact solutions satisfy boundary conditions, and these functions too satisfy this boundary condition. But inside the domain, if I take any point inside the domain, omega is positive, and meaning this relation, I give these functions. So in any point exist these functions. It was not happen if I use something, functions which is not positive inside the domain. Because, for example, when I consider such domain, and if I, for example, multiply sides of this boundaries, then I receive functions which also satisfy boundary condition if this condition is 0 in that case. But I cannot use structure that kind in that case, because these functions which I took as multiplications sides and sides this boundary, these functions will be 0 here. And in any choice functions phi, I cannot do any other meanings which can be in exact solution. Further, we shall see that problem of completeness and fullness using meanings, or constructive meanings, is the problem very important and sometimes very difficult. Now, this problem when functions is equal something on the boundary is called Dirichlet problem. Problem Dirichlet. But now we consider another problem. Sometimes in boundary conditions we have, for example, such on the boundary are given not functions, but, for example, normal derivatives, or more complex boundary conditions. For example, in theory of plates and shells, sometimes are meaning such conditions. Here is third order derivatives along the normal. Here is not only derivatives, but tangent derivatives. system such, not one derivative, but system conditions on one the side can be. Or on one side of the domain, derivatives one type and one kind and other different kind. But idea I shall explain on this example. What difficulties is when we constructing structure of solutions or bunch of the functions which satisfy boundary conditions, we constructing functions which have sense in all domains, but this boundary condition is connected with normal derivatives. Normal derivatives is definite on the boundary. But how to take into consideration this information in construction which must satisfy all boundary conditions and have sense inside the domain? In what way to do? Maybe somebody have some idea how to overcome this problem. This is a problem, and when I was a young man, not 70, but about 30, and I have reported on this problem in our scientist circles, they agree with me, but always say, of course, you can construct such formula when functions is known on the boundary. But in that case, all your theory cannot be used. You cannot construct such formulas. But let us remember that we not only can write equations of the boundary, but can also construct such equation which is normalized. So we can construct such functions which is equal on the boundary, positive inside the domain, and also we can construct such functions which have such property. This is conditions which we call normalized equations of the boundary. But look here, what this means for us. Suppose this is a boundary, here is normal, and functions which we considered positive here, which we omega, but gradient omega. We once talking about that. Of course, gradient is always normal to the equipotential functions, or equipotential lines. But 0 is one of the potential lines. That here functions is positive, so gradient is have the same directions than number. But we have such conditions, so gradient and derivatives along number are the same. So normal and gradient have the same unit longitude. But normal along derivatives this is formula for derivatives on directions nu. But gradient omega is S gradient omega and normal is the same vector, we can write that du, the nu, is on the boundary. On the boundary, it will be the same as cosine nu or x. This is this vector and nu. This is cosine between nu and abscissa x. This is cosine, and they coincide. This is cosine z, and this is cosine z on the boundary. But look here. This operator is definite only the boundary. But these functions, which coincide with this operator on the boundary, have sense everywhere inside the domain. This is first step in the right direction. So, if we introduce such operator, then on the domain will be this operator denoted in such way can be is equal derivatives second order along the normal. But if I wanted to receive mth order, oh yes, you are right. Oh, I put here, for nth order, I can receive such. I write it in operator form. If I wanted to receive nth order derivatives along the normal, I must use binomial formula, and that on these three places put functions O. For example, for second order, we shall receive d omega or dx square so on. For tangent derivative. I shall consider only, for simplicity, only 2D space for tangent derivative of the boundary. Or we can noted it as symbol T capital sub 1. So in our function theory, there were constructed such kind of operators. Due to them, we can symbols derivatives which define only the boundary, introduce inside the domain. And using this operator, we can construct a lot of useful things. Some of them I explained you. Only I shall show results without proof them because it is a long way to write these provings. I only shall try to explain results on intuitive level as I appeal to your intuition. This lemma led us to, if we knew normalized equations of the boundary, constructed n times normalized equations of the boundary. I remind you that if besides the conditions satisfy such conditions, on the boundary, then we call such functions or such equations n times normalized equations of the boundary. High is the degree m, the nearer such functions is to normal functions of the boundary. But it is they have to new functions which satisfy these conditions to constructed functions which satisfy these conditions. The recurrent formula is such way. Suppose 2 times normalized equations or normalized functions expressed through 1 times or normalized So if we knew 1 times normalized equations of the In that way, we receive 2 times normalized equations, and so on, n times normalized equations. Such formulas. These formulas can be given as program, and computer can use these formulas, receive n times normalized equations for any drawing. For example, we knew normalized equations for the circumference. For example, radius is such circumference, radius 1. Center. But for finding second order derivative functions, we must construct it 2 times, will be omega 1. So these functions minus and d2 sub 2 from these functions. D sub 2 has inside such derivatives. And x squared and d1 d squared in this formula for d2 here. If it one time derivative this formula according to x, we receive minus x, and second order will be minus 1. The same for y, but 5y. And d2 omega 1 will be minus 1, and the omega, it will be x squared. The omega, according to x, it will be minus x, and in square, it will be x squared. And the same for y squared. Next derivative is 0. So this is, we must multiply this minus x squared plus. This is 2 times derivatives equations of the circumferences. Что? Еще в квадрате есть. Square. Thank you very much. So this is a simple way, but if we have large formulas, this is difficult way for man. But computer can solve this problem without any difficulties. And it is good thing that for constructing boundary structure of solutions, we have not, as a rule, very high derivatives in boundary condition. Second, third, fourth, and in one only times I met 8 derivatives, but it was unique problems. Now, another result. Suppose we have derivatives nth order. Nth order normalized. And consider such formula. Omega n multiply phi, and let us take derivatives from here, some order. Then, excuse me, suppose it will be, just like the idea, write symbols. Suppose this is nth order. Normalize. But take here some degree, such formula. Then it will be equal m factorials phi or 0 if s is equal m and s less than m. It is easy to guess why that happened. If we have derivating such product, then only if the derivatives first term, first factor, then we can reduce the degree. And only if we take derivatives m times, we receive such formula. On the, of course, on the boundary. If we take derivatives less than m order, then it will be here m in some degree, positive degree, and it will be 0 on the boundary. This is very simple result, so this is lemma 2. And then, what kinds of lemma? I must look here. Oh, this is not lemma, but theorem. New notion. I don't know how to translate, nor in Russian, normalizant. In English, I don't know. Suppose normalizant. Normalizing, maybe. Normalizes. So,
normalizes other functions.
I don't know what letter here, right? Z or Z. Suppose we have some functions. For simplicity, I shall explain on two-dimensional space. Suppose we have some functions which is derivative several times, so times if it needed. And we have omega functions, which is n times normalized. Then normalizant functions f according to functions phi is such expressions. And such normalizant is denoted by such symbol star. These functions normalizant have such interesting property. Normalizant on the boundary coincides with f on the boundary. It is evident because this is 0, omega is 0 on the boundary, so we have such coincide. But if I shall take derivatives, it will be 0 if s is 1. What kind? According to the, if this is functions m times normalized, then it will be till m will be 0. So this is functions. Normalizant is the functions which coincide with given functions on the boundary, but all other derivatives, according to the normal, till some order, are 0. This is useful property, and this property let us to write such kind of formula. Suppose theorem. Suppose we knew that functions f on the boundary is coincide with some functions f sub 0. Then coincides with k on the boundary. And k is 1 till n. So suppose the functions considered have no meaning on their meaning on the boundary. Function is f coincide with f o on the boundary, and derivatives along the normal coincide with given functions. Such informations. Then we can write such formula. In 1D, in one-dimensional space, if we take gamma is point, omega is x minus x o, equation this point, then we receive from this formula usual Taylor formula. Suppose, excuse me, omega. This is a residual term. In one-dimensional space, we receive from this usual formula. In n-dimensional space, we also receive usual formula Taylor for one point if we take equations such kind x minus x0. This is normal in n-dimensional space. So this is such equation x1 minus x. this is coordinate of x sub 0, this is coordinates point x. In that case, we also receive the usual Taylor's formula. But in general case, we constructed functions omega in such way that if this is boundary, then according in some vicinity of the boundary, these functions along the normal behave themselves as distance. So as in such way, this is a distance between point on the boundary and any point in vicinity. So this idea, which were put in the Taylor's formula, using here due to our knowledge to constructing normalized equations of the boundary. This generalization Taylor formula, we so called generalized Taylor's formula. This result let us constructed structure of solution for different kinds of boundary conditions. For example, if I show 3 minutes and I show how to construct a structure of solution for these conditions. They call Neumann conditions. Neumann boundary conditions or Neumann problem. We knew only first derivatives, but we knew what we don't know. We know first derivatives, but we don't know what means have functions on the boundary and what other derivatives are on the boundary. We only have that kind of information. So we can use this formula to the first order, and we shall have such result. The functions, we don't know what is this functions for functions. We know that this is, for example, in such way, but we must take normalized. Then next term, this unit, then derivatives is phi, so we must decide phi normalized multiplied on omega and omega square for such indefinite component. This is not known functions, but we knew that here is normalized and here is normalized. So we must write phi x minus omega d omega dx, y omega d omega dy plus phi the same x minus omega y multiply phi omega multiply omega x y and plus omega square phi 1. We have in this formula two indefinite components. So we can consider even this formula as structure of solutions. But here we can transform this formula in another in another form. We can, for example, consider usual formula Lagrange in the vicinity of the point x, y. So we can write x, y minus omega dx here is SH1, H2. This is, and this is such kind of representations. X plus H1 plus H2. This is according to the known formula. This is xy, then plus H1 dphi dx plus and so on. You know this formula. So in that way, if we put instead H1 and H2 to these expressions, we receive these expressions plus second order in this formula, residual terms, and in this we receive the same. And residual term the same order. So I don't write it and include in this term, and plus, and we denoted these formulas as D1 operator. So we, as a result, receive the same formula phi minus omega d1 phi plus omega d1 phi and plus omega square phi 1. But maybe it seems that I mistake in some place. Of course I mistake. No. And here is multiplication on omega. So this is second order small omega and omega, and we can these three terms put here, and this is I mistaken, so we have such kind formula omega p. Here also omega I miss. And this formula, which have two indefinite functions, a lot of times was using in different kinds of mathematical physics problems. This formula was investigated from point of view compactness and fullness, and we have optimistic results in that. We see that when we're constructing this formula, we have разложение. We have expansion along the degrees of omega in the same way as it was done at Taylor's. Excuse me, I must finish. I took a lot of time from you. Thank you very much for your attention.
What are you doing next time?
Next time I finish